At the European Organization for Nuclear Research, humanity operates a 27-kilometer ring designed to test the limits of physical matter. Inside these detectors, hundreds of billions of protons collide at near light speed. These impacts generate localized heat capable of melting half a ton of copper. Human engineering has yet to destroy a single proton, despite the immense kinetic energy focused on these individual particles. These sensors record the fracture of internal bonds, but they have never captured the total annihilation of the particle itself. The most extreme kinetic forces humans can currently generate remain entirely ineffective against this basic building block of the universe. To understand this resilience, we have to look past the scale of our machinery and into the microscopic geometry of the atom. If a hydrogen atom expanded to Earth size, its proton would only match the Great Pyramid of Giza. This structure is almost entirely empty space. Inside this void lie 3 quarks. While carrying significant mass, they operate as dimensionless points with zero physical area. These 3 infinitesimal points emerge from high-energy collisions unscathed, surviving forces that should, by the logic of the macroscopic world, tear them apart. The strong nuclear force acts as an invisible mathematical bind, locking these 3 points in a configuration that no external energy has been able to break. Because protons are mostly empty space, they will usually just pass completely past each other during an acceleration cycle. A direct hit between these particles is rare, but when it occurs, it produces a shower of over 100 particle fragments. Quarks are never found in isolation. They are bound to at least one partner. When a collision attempts to rip a quark away, the strong force resists. As tension peaks, the kinetic energy condenses into mass, generating a new quark and antiquark pair. Extreme impact triggers a spontaneous conversion. The energy of the collision precipitates into new matter, healing the proton structure as quickly as it is disturbed. The newly created quark instantly replaces the one ejected by the impact, restoring the proton to its original state. The ejected quark immediately binds with the remaining antiquark to form a temporary particle called a meson. Mesons exist for only nanoseconds before breaking down. This decay chain fractures the meson into lighter particles, eventually resolving into electrons, neutrinos, and finally pure photon energy. Particle accelerators create a brief display of decaying fragments, but the core proton emerges from the experiment intact and unchanged. Reaching a state where the strong force fails requires a journey all the way back to the very beginning of time. Fractions of a second after the Big Bang, the universe consisted of a high-energy quark-gluon plasma. The background heat of the infant universe was so extreme that it overpowered the strong nuclear force, preventing quarks from binding into stable particles. As the universe expanded and cooled, the strong force became the dominant influence, permanently locking quarks into the protons we see today. Quarks remain trapped by the cooling of the cosmos unless we can replicate the infinite heat of those first moments. Antimatter is the only known mechanism in the modern universe for the total destruction of a proton. Matter and antimatter annihilation is a complete conversion where 100% of the mass is released as pure energy. This chart shows the scale of that release. Mixing 1 gram of hydrogen with 1 gram of antihydrogen produces 43,000 tons of TNT. Our current capabilities are limited to trapping 80 atoms for 17 minutes. Synthesizing a single gram would take 10,000 years. High-energy collisions create matter and antimatter in equal amounts, yet the observable universe consists almost exclusively of regular matter. Our existence depends on this durability. We are the stable remnants of an ancient cosmic imbalance, preserved by a force that refuses to let matter be undone.